Decoded.
Welcome, everyone, to Book Decoded.
Great to be here.
Today, we're jumping into Govert Schilling's Target Earth, and let me tell you, it's quite a ride.
It really is. Not your average astronomy book at all.
No, definitely not. This is all about, well, stuff hitting our planet. Sometimes little bit, sometimes much bigger deals.
Yeah, the book does a great job mixing the history of how we even realized things could fall from space with, the actual science and the potential risks.
Right. It's this story of discovery, but also, like, becoming aware that we're kind of in a cosmic shooting gallery.
A bit dramatic, maybe, but not entirely wrong.
So we're going to unpack some of the wildest stories, someone getting hit by a meteorite while napping.
Oh yeah, Anne Hodges. We have to talk about her.
And the sheer power of impacts that literally changed the planet, changed life itself. Get ready for some whoa moments.
Definitely. So where should we start? The small stuff hitting us.
Yeah, let's start there. Because the book makes it clear, this isn't just ancient history. Space rocks land all the time.
They do. And Anne Hodges in 54 is maybe the most famous direct human encounter. Through the roof, bounced off a radio, hit her on the hip. Incredible.
Just imagine. And for so long, people just refused to believe rocks could even fall from the sky.
Right. Total skepticism. Schilling points to the L'Aigle meteorite shower in France, 1803, as a real turning point.
Because it was so well documented.
Exactly. Jean-Baptiste Biot investigated, collected witness accounts, found the fragments. It became scientifically undeniable.
Before that, even reports from, Ming Dynasty China or suggestions like Chladni's in the 1790s were just dismissed.
Pretty much. It took seeing it happen repeatedly and having scientists confirm it.
And there have been other near misses, right? The book mentions people on a beach in Australia.
Yeah, Binningup Beach, 1984, landed just a few feet away. And then there's the Peekskill meteorite in 92 that famously hit a parked car.
Huh. I remember seeing pictures of that Chevy Malibu.
Makes for a good story. Thankfully, no one was hurt in those cases, which is actually pretty typical.
It seems incredibly rare for someone to actually be killed by one. The book mentions one confirmed case.
Just one really solid case, yes. An Iraqi man in 1888. Considering how much stuff falls, it shows you how big the Earth is and how much of it is unpopulated or ocean.
Still, even places like the Netherlands, relatively small, have had documented falls. Glannerbrug, Brook in Waterland.
Diepenveen, too, though that one fell much earlier and was found later. It happens everywhere.
And globally, tens of thousands have been found, hundreds of tons of material.
That's right. There's even a market for them. Collectors pay serious money for certain types.
What types are there mainly?
Well, broadly, you've got iron siderites, which are only about 6% of falls, but are often easier to recognize. Then the vast majority are stony meteorites.
Like chondrites and achondrites.
Exactly. Chondrites are particularly interesting because they contain these tiny ancient spheres called chondrules, basically unaltered building blocks of the solar system.
How do people even spot them? What are the clues?
Schilling lists a few key things. Often a dark fusion crust, where the outside melted during atmospheric entry. Some are magnetic.
Okay.
Congrules, if you can see them. Sometimes these sort of thumbprint-like depressions called regmaglyphs. And in irons, if you cut and etch them.
You get those amazing Widmanstetten patterns.
You do. That distinctive crystal structure that forms only with incredibly slow cooling, like inside an asteroid core over millions of years. You can't fake that on Earth.
Wow. So finding one randomly is tough, but if you see a fireball...
Then the odds get better. Like the Winchcombe meteorite recovery in the UK in 2021, people filmed the fireball, scientists calculated the trajectory, and folks found fragments pretty quickly.
And Peter Jenniskins, the book mentions him predicting impacts.
Yeah, he's had incredible success. Asteroid 2008 TC3 was tracked before it hit, and he led the search in Sudan and found the pieces. Same again in Botswana with 2018 LA. Amazing work.
It's like celestial CSI.
Kinda, yeah. And then you have dedicated programs like Anna's Met searching in Antarctica.
Why Antarctica?
Because meteorites, especially dark ones, stand up incredibly well against the blue ice. And the ice flow concentrates them in certain areas. It's a meteorite gold mine.
Makes sense. And it's not just big rocks, right? Micrometeorites.
Constantly raining down. John Larson even figured out how to find them on city rooftops in 2016. Billions hit Earth every year.
So from tiny dust specks to things like the Hoba meteorite in Namibia.
Over 60 tons. The largest single piece ever found, just sitting there. It really drives home the scale.
Okay, so we have all this stuff hitting us. Let's clarify the names. It gets confusing.
It really can. So out in space, it's a meteoroid.
Right. Little chunk of rock or metal.
Then, when it hits our atmosphere and streaks across the sky, that flash of light is the meteor, what most people call a shooting star.
Okay, meteor, got it.
If it's really bright, exceptionally bright, is often called a fireball or a bolide. Same phenomenon, just brighter.
And if a piece survives the fiery plunge and lands on the ground?
That's the meteorite, the actual physical object you can pick up.
Meteoroid, space, meteor, sky flash, meteorite, meteorite, ground. Simple enough.
Mostly. Though Schilling points out even astronomers sometimes blur the lines, like calling 2008 TC3 an asteroid right until it hit.
Ah. So what is the difference between a meteoroid and an asteroid, technically? Size?
Generally, yes. Asteroids are larger bodies orbiting the sun, too small to be planets, but bigger than meteoroids. Think Ceres, the first one discovered back in 1801.
By Piazzi, they thought it was a planet at first, didn't they?
They did. It took William Herschel observing more of them to say, hang on, these things look star-like.
Yeah.
Asteroid, not like planetary disks. He reclassified them.
And now we know there are millions.
Over 1 million cataloged, yeah. But their total mass is tiny, like 3% of the moon's mass.
Yeah.
Mostly concentrated in the main belt between Mars and Jupiter.
Leftover building materials from the solar system's formation?
Essentially, yes.
Yeah.
Rocky remnants that never quite formed a planet,
Right.
largely due to Jupiter's gravitational influence.
And they get names, right? Temporary ones, then permanent ones.
Yep, a whole system. And they're not all in the main belt. The book talks about near-Earth asteroids, or NEAs.
Those are the potentially hazardous ones?
Potentially, yeah. Their orbits cross or come close to Earth orbit. There are different groups, Apollos, Amors, A10s, Ateris, based on the specifics of their orbits.
And Trojans, are they near Earth?
No, Trojans share orbits with planets, mostly Jupiter, clustering at stable gravitational points called Lagrange points, ahead of and behind the planet.
Asteroids seem pretty diverse, too. Some spin incredibly slowly, some super fast.
Oh yeah, the book mentions one taking 78 days to rotate, another 2014 RC spinning every 16 seconds.
Whoa, and orbits vary wildly, too.
Absolutely. Some stay close to the sun, some swing way out. It's a very dynamic population.
Okay, so that's asteroids. What about comets, the icy ones?
Right, the dirty snowballs, as they're sometimes called. Mostly ice water, methane, ammonia, carbon dioxide mixed with dust and rock. They tend to have much more elongated orbits than asteroids.
And they only look like comets when they get close to the sun.
Exactly. The sun's heat vaporizes the ices, creating that fuzzy cloud around the nucleus called the coma.
And the tails.
The solar wind and radiation pressure push that gas and dust away from the sun, forming the tails. Interestingly, the tail always points away from the sun, regardless of the comet's direction of travel.
People used to think they were bad omens, right?
For centuries, until astronomers like Tycho Brahe showed they were distant celestial objects, not atmospheric things, and Edmund Halley figured out they could have predictable elliptical orbits.
Like Halley's Comet itself. But bright comets we can see easily, like Neowise a few years back, they're pretty rare.
They are, unfortunately. Most are faint. But the debris trails they leave behind.
Give us meteor showers like the Perseids from Comet Swift-Tuttle.
Precisely. When Earth plows through that stream of cometary dust, we get a meteor shower, appearing to radiate from a specific point in the sky. The radiant, in this case, the constellation Perseus.
So cool how it's all connected. Asteroids, comets, meteor showers.
And beyond that, you have the Kuiper Belt objects out past Neptune, including Pluto. Then the even more distant Oort cloud, this vast reservoir of potential comets.
And even interstellar visitors like Oumuamua and Borisov.
Yep, objects from entirely different star systems passing through ours. The lines can even blur sometimes between asteroids and comets. Some asteroids show comet-like activity.
But the bottom line, as the book emphasizes, is that many of these objects, whatever we call them, could potentially hit Earth.
That's the crucial point. And Earth has the scars to prove it's happened before.
Let's talk about those scars, the impact craters. Schilling mentions a relatively recent discovery in China, Yulon Crater.
Yes, identified in 2021, I believe. Quite large, over a mile wide, but heavily eroded because it's in a forested, geologically active area. Quite young geologically, maybe 50,000 years old.
How does that compare to, say, Meteor Crater in Arizona?
Meteor Crater is smaller, but much, much better preserved because it's in a dry desert. Very little erosion. It looks almost fresh, even though it's also about 50,000 years old.
And that's the one Daniel Barringer was convinced was an impact crater, against the prevailing volcanic theory.
He was. He spent years drilling, trying to find the main mass of the meteorite, which wasn't really there because it mostly vaporized. It took Eugene Shoemaker in the 1960s, finding minerals like coesite and stishovite forms of quartz, shocked by immense pressure, to definitively prove the impact origin.
That shocked quartz seems to be a key fingerprint.
It is. The energy release in these impacts is staggering. Kinetic energy converts violently into heat and shock waves, creating these huge explosions and circular craters. It's like a bomb, but cosmic.
Shoemakers even use bomb craters to train Apollo astronauts, right?
He did, at Sunset Crater Volcanic Field, which has features somewhat similar to impact craters in the moon.
Are all impact craters huge like that?
Not at all. Schilling mentioned smaller ones, like Caracas in Peru from 2007. A stony meteorite hit made a crater maybe 40–50 feet across. People nearby got sick, possibly from arsenic and vaporized groundwater.
And Chelyabinsk in 2013, that didn't make a big crater on land, did it?
No, that was mostly an airburst. The main body exploded high in the atmosphere. The shockwave broke windows and injured over 1,000 people. But the fragments that landed were relatively small. A larger chunk made a hole in lake ice. If it had been bigger or made of iron, it could have reached the ground intact and made a significant crater.
Like Tunguska in 1908.
Possibly. Tunguska was a massive airburst over Siberia, flattening maybe 800 square miles of forest. Still debated whether it was a comet or asteroid fragment and whether Lake Checo might be a related impact crater. But no large crater like meteor crater was formed.
So there's a difference depending on size and composition. Small stuff slows down, big stuff doesn't.
Exactly. The atmosphere is a great shield against smaller meteoroids. They burn up or slow down to terminal velocity. But objects tens of yards across or bigger punch through with most of their cosmic speed, hitting the ground with enough energy to excavate a crater.
Some of these craters even feature in indigenous legends, don't they?
Oh yes. The Henbury craters in Australia, maybe 4,700 years old, figure in Aboriginal Dreamtime stories. The Kali craters in Estonia, about 3,500 years old, likely influenced Finnish and Norse mythology. People witnessed these events.
And the book lays out the scary frequencies, Chelyabinsk size every 50 years or so.
Roughly. Tunguska size maybe every 750 years. A 100-yard object making a half-mile crater maybe every 5,000 years. It gets rarer as the size increases, but the consequences get much, much worse.
A half-mile wide object hits every 500,000 years or so, making a crater over 5 miles wide. That's civilization altering.
Or ending. Widespread devastation, tsunamis if it hits the ocean. It's serious stuff. Schilling even touches on theories linking impacts to events like the destruction of Sodom and Gomorrah.
Wow. And then there are the ancient giants, Nördlinger Ries in Germany.
Huge. About 15 miles across, 15 million years old. Formed a natural basin where towns are now built. There's evidence it might have been a double impact, with the smaller Steinheim crater nearby.
And others. Rushmort in France, Siljenring in Sweden, Manicouagan in Canada.
Manicouagan is spectacular from space, that huge ring lake, about 45 miles across, from 214 million years ago. But erosion takes its toll. Finding very old craters is hard.
Except for the truly immense ones. Sudbury, Redifern.
Yeah, Sudbury in Canada, originally maybe 80 miles wide,
Yeah.
1.85 billion years old, now famous for mining nickel and copper metals concentrated by the impact. And Vredefort in South Africa, the largest confirmed structure, maybe 100, 200 miles originally, 2 billion years old. Just the central uplift, the Vredefort Dome, remains prominent.
Incredible scales, but the most significant one, at least for us mammals.
Has to be Chicxulub, the dinosaur killer.
Right. Schilling really dives into this. Our existence is basically owed to that event 66 million years ago.
It's hard to overstate its importance. Dinosaurs ruled for 160 million years, then suddenly gone, along with about 75% of all species on Earth. The KPG boundary event.
And the key was the Alvarez hypothesis in the late 70s, early 80s.
Luis and Walter Alvarez, yeah. They found this thin layer of clay right at the KPG boundary, worldwide, packed with iridium.
Iridium being rare on Earth's surface, but common in asteroids.
Exactly. Their calculations suggested a massive asteroid impact, maybe 6 to 10 miles wide, kicked up enough dust and iridium to form that global layer. Jan Smit in the Netherlands found similar anomalies independently around the same time.
So what actually happened during the impact?
Unimaginable energy release. A yottajoule, the book says. The asteroid and a huge chunk of Earth's crust vaporized instantly. Material blasted into the stratosphere, blocking sunlight globally.
Causing massive immediate fires, then a prolonged impact winter.
Yes. Global wildfires ignited by re-entering debris, then years of darkness and cold. Photosynthesis collapsed on land and in the oceans. Food chains crumbled.
It wasn't just the dinosaurs, but marine reptiles, ammonites, so much life.
Wiped out. Mammals, being mostly small and possibly burrowing, survived and then diversified into the niches the dinosaurs left vacant.
Now, there was an alternative theory, wasn't there? Volcanoes.
The Deccan Traps in India. Massive volcanic eruptions were happening around the same time, releasing huge amounts of climate-altering gases. Some argue that was the primary killer.
But the Chicxulub crater discovery sealed the deal for the impact theory.
It was the smoking gun. Found partially offshore in the Yucatan Peninsula, dated precisely to 66 million years ago. The evidence compiled since is overwhelming. Shocked quartz, not just iridium. Melted glass spherules called microtectites rained down thousands of miles away. Traces of a mega tsunami around the Gulf of Mexico. Even fossil fish found choked with impact debris from the tsunami surge. Drilling into the crater's peak ring confirmed the impact models.
So impact is the primary cause, though maybe the volcanoes didn't help.
That's the general consensus now. The impact was the knockout blow. Some research suggests the impact's seismic waves might have even intensified the Deccan volcanism, a sort of double whammy. But the impact alone was catastrophic enough.
Have other mass extinctions been linked to impacts?
It's debated, but the evidence isn't nearly as strong as for the KPG event. There have been other major extinctions, like the Permian-Triassic Great Dying, but no definitive impact crater or iridium layer has been convincingly linked.
What about that theory of extinctions happening periodically every 26 million years or so?
Ropp and Sepkoski proposed that based on the fossil record. The idea was maybe something regularly disturbs the Oort cloud, a hypothetical companion star to the Sun, or the solar system passing through the galactic plane sending waves of comets inwards. But there's no strong evidence for a companion star, and the periodicity itself is debated.
So the KPG impact seems unique in its clear link to a mass extinction.
In the geological record we have so far, yes, it shows Earth is resilient in the long run, but the biosphere life itself can be incredibly vulnerable to these cosmic events.
And now, unlike the dinosaurs, we're actually aware of the danger.
That's the crucial difference Schilling emphasizes. We understand the threat. We're starting to map the potentially hazardous objects. We have the potential to act.
So, wrapping up our look at Target Earth, it's clear our planet isn't just floating in serene isolation, is it?
Not at all. It's part of a dynamic, sometimes violent, cosmic neighborhood. We're constantly interacting with debris, and occasionally that interaction is dramatic.
Yeah, the book really paints that picture vividly. From historical impacts to, the science of tracking near-Earth objects today, it feels like a story that's still unfolding.
It absolutely is. It highlights how connected everything in the solar system is, and how these external events have profoundly shaped Earth history and the evolution of life.
It really does change how you see things. Even just a quick shooting star makes you think about where that little speck came from, its journey.
And the bigger picture it represents.
Target Earth is just fantastic if you're curious about all this. Seriously, grab the book for way more detail than we could cover.
Definitely recommend it.
So, thinking about all this, what's the one thing that makes you look up at the sky differently now? We'd love to hear your thoughts, too. Join the conversation.
Yeah, what resonates with you?
Thanks so much for tuning in to Book Decoded. Until next time, keep looking up and keep that curiosity alive.